Quick revision video on coordinate bonding, also known as dative covalent bonding. So we'll start with the essentials. A coordinate or dative covalent bond involves a shared pair of electrons between two bonding atoms where one atom supplies the pair of electrons. In dot and cross diagrams, the coordinate bond is shown by an electron pair of the same type. So two dots, two crosses, that sort of thing. In displayed diagrams, the coordinate bond is shown by an arrow pointing away from the atom, supplying the electron pair. So we're just going to work through some reactions where a dative covalent or a coordinate bond is formed. I'll explain what's going on, and then there's a couple of questions at the end for you to try. So the first example is between ammonia and hydrogen chloride. So we've got the dot and cross diagram here. Got the reaction there, so you can see it forms ammonium chloride. So what's going to happen is the hydrogen chloride is going to donate hydrogen, but it's going to donate it as a proton or an H+ ion. So it's going to leave that electron behind, and the H+ ion is going to bond with the lone pair on the nitrogen of the ammonia molecule. So the upshot of that looks like that. So we've got an ammonium ion formed. It's got a positive charge because if you think about it, an H+ ion has come over, so the charge is incorporated into the ion, and the chloride ion is negatively charged because effectively the chlorine's gained that electron as the hydrogen left it behind, so it gets a 1- charge. So there's that coordinate bond. You can see the pair of electrons of the same type from that nitrogen atom. And you can represent the ammonium ion like this. So this is a displayed diagram. So we've got the regular covalent bonds, 3 of those, and there's that coordinate bond there. So the arrow points away from the pair of electrons that's being supplied. Next example is the reaction that occurs when you dissolve hydrogen chloride in water to make hydrochloric acid. So we'll start with the dot and cross diagram. So hopefully you can appreciate what's going to happen. The hydrogen chloride again is going to donate this hydrogen as a proton, an H+ ion. It's going to bond with one of the lone pairs on the oxygen. It's going to leave behind that electron, so this will become a chloride ion. So there's the upshot of that. So this ion formed, the H3O+ ion, is called the hydroxonium ion. Positively charged for the same reason as before, because a proton and H+ ions come across. Negatively charged chloride ion because the hydrogen's left its electron behind. There's the coordinate bond, so we've got the same type of electron, both belong to the oxygen, and the displayed diagram looks like that. And obviously we've got a lone pair still on the oxygen, so we would show that as a double dot. So if we just move on to the equation now for the process, so there it is there, H2O plus HCl gives the H3O+ ion and Cl-. Now that's often simplified to this, which I'm sure you've seen before. So if you put hydrogen chloride in water, you end up with an aqueous H+ ion and aqueous chloride ion. Now technically the individual proton, the H+ ion, is too reactive to actually exist, but it's an accepted abbreviation for the hydroxonium ion. And the third reaction is between ammonia and boron trifluoride. So you can see we've got the dot and cross diagrams there. I'm sure you can see already what's going to happen. We've got an electron deficient boron atom. So only 6 electrons in that valence shell. And we've got a pair of electrons, a lone pair on the nitrogen. So we can get a coordinate bond formed between the boron and the nitrogen. And that's going to form this new compound, BF3NH3, which would look like that. And there's that coordinate bond. Okay, so we'll finish with this couple of questions about coordinate bonding. So you've got some information there about carbon monoxide and nitric acid. So if you want to have a go at that, just pause the video and then press play when you're ready for me to go through the answers. Okay, so carbon monoxide first. So the way this works is you put 2 electrons, so the blues belong to the carbon, 2 electrons from the carbon and 4 electrons from the oxygen. So if you think about it as you've got like a regular double covalent bond and then a coordinate bond on top originating from the oxygen, and so you've got a triple bond overall between the carbon and the oxygen. So there's the coordinate bond highlighted there. And the nitric acid looks like that. So we've got regular covalent bonds here and here. We've got double covalent bond here, and there's that coordinate bond between the nitrogen and the oxygen.